Today we're going to look at a definite integral that's kind of a weird form, at least for us to be able to use this fundamental theorem to evaluate it. We're going to have to rewrite the form using the definition where we have this absolute value. And then we'll take a look at what the absolute value graph, the graph of this function looks like, and how the graph relates to the definite integral value. So first of all, we need to think about what this absolute value function form would be. Now, the idea here, we'll look at the definition of the absolute value. We'll just start with the absolute value of x. And it depends on what x is as to what the output would be. If x is positive, absolute value of, say, 3 is what? 3. So if x is positive, then the absolute value of x will be the exact same as what the inside is. And that's true for x being greater than 0. We could also say that's true for x equaling 0. Absolute value of 0 is 0. Okay. But what about x being a negative number? If x is negative 3, what's the output? Okay, absolute value of negative 3 is positive 3. Now, in terms of algebra, we need to look at this a little differently than what we expect. We're going to write this as not negative x, but think of this as the opposite of x. So if x is negative, the opposite of x would be positive. So we represent the definition of the absolute value as this piecewise defined function. And if x is negative, the output's going to be positive, which is the opposite of the input. So that little dashed line can actually represent 3 different operations. In this case, it's the opposite of. A lot of times we think of it as subtraction or negative, but technically this isn't negative x, this is the opposite of x, which is a negative value. I know that sounds more confusing, but by this definition then, we're going to represent our function, and in this case we kind of have to, well, think about what the absolute value of the quantity x minus 3 will be like. And if you want, we could rewrite it as this piecewise defined function. This time, instead of looking at kind of 0 as the break, the switch between positive and negative, what x value are we going to need to use? Okay, 3. When x is equal to 3, we get 0 on the inside. And then anything greater than 3, we could say if x is greater than or equal to 3, our output will be x minus 3. So what's the second part then? Okay, we have to say the opposite of. Now, it's the opposite of the entire inside. So the opposite of the quantity x minus 3 when x is less than 3. Okay. And for that part, if we want, we could multiply the negative through make it negative, well, negative x, or opposite of x, how about that? Opposite of x plus 3 would be that part simplified. And then finally, the entire function we're looking at, it's that absolute value and then minus 4. Let's go ahead and put that on top of the next page. So the first part will be very straightforward, as positive values are with absolute values. We have the inside minus 4 for x being greater than or equal to 3. And then we said the bottom would simplify to negative x plus 3, or opposite of x plus 3. And then we have the minus 4 for our original function, the integrand. And that's going to be true for x is less than 3. So f of x, the function that we are integrating, can be represented as this piecewise defined function, and we can actually simplify it a lot more. Of course, x minus 3 minus 4 we can just write as x minus 7, and then the second part, opposite of x minus 1, will represent the function value when x is less than 3. Okay. So, what does that mean when we take a look at it in terms of this definite integral? Well, because of the change at the value of 3, we're going to need to separate this into two different parts. We'll go from 0 to 3, and what's the integrand for that part? Okay, that's going to be when x is less than 3, so we'll be integrating negative x, or opposite of x, minus 1. And then the next part would be from 3 to 6, and we integrate what? Okay, the x minus 7. The function output when x is greater than or equal to 3. So now we've turned this weird-looking integrand into some very simple integrands, but we had to separate it into the two parts by the definition of the absolute value. Questions up to this point? So now we're finally ready to integrate, evaluate the integrals, and to do that, all we really need to do is find the antiderivative of the opposite of x, or negative 1 times x, and we can say antiderivative of x is x squared over 2, using our power rule. Antiderivative of minus 1, just minus x. And again, to quickly check this, take the derivative of what we have here, and we should end up with negative x minus 1. Hopefully we can do that quick enough. And in this case, we evaluate it from 0 to 3. Now, notation-wise here, we're evaluating two different terms for that same interval, so I like to put brackets around it, grouping symbol saying it goes through all of these terms. And then the second part, again, two different terms here, antiderivative of x and antiderivative of 7. And then we evaluate that from 3 to 6. Okay. Well, the fundamental theorem tells us to do what once we get to this point? we start with 0 or do we start with 3? Okay, we start with the top one, f of 3. Okay, so plug 3 in for x. Then we subtract f of 0. Now, we got to be careful here because we're subtracting that entire quantity. Now, the nice thing in this case, when we plug 0 in, what do we get? 0. Now, that doesn't always happen when we plug 0 in. So make sure that you double check if x is 0, does the result end up being 0? Okay, a lot of times it does, but not all the time. And then the last piece, well, this time we start with 6. And then this time we will have something to subtract. Plug 3 in. And as usual, run out of room. I think these are easy enough calculations. You can see what it should be, even if you can't read what I write. So as we go through this, let's see, 36 over 2 minus 42. And then when we're subtracting, be very careful here. A lot of opportunity for little mistakes. We'll have minus 9/2, but then minus a negative 21. So plus 21 there. And as we combine all of this, give you a chance to work at it. Sometimes it's easier to go ahead and group the negative values together and the positive values together. And again, those two will give us that negative 9. So we end up with what? We'll end up with a negative, is it negative 15? Now, make sure you check my values here. Okay. Now, think about what we've been doing with the definite integral. We've been using that to find the area under a curve and above the x-axis. And we've been getting positive values for that answer. Well, area would be considered to be positive. We can't have a negative area. Can you imagine? Think about that for just a second. What kind of a world would have negative area? Okay, quit thinking about it because it might blow your mind. But the definite integral, like I've been saying all along, is a mathematical operation, and one of the applications it is used for is area. Sometimes it doesn't equate exactly to that area. Well, in this case, we can relate it to area, but it's going to be a little different situation than we have been looking at. So let's take a look at the graph of this original function, this absolute value function. What kind of a graph do we find with an absolute value? Okay, it's the V shape. And in this case, if we can, oh, nice straight line there. Well, imagine that that's a straight line. In this case, the kind of, I guess we could call it the vertex of the V. The bottom of the V would be at what point? Okay, 3, -4. When x is 3, y is going to be at -4. And again, algebraically, we said things were going to change at x equals 3. Well, what we find, well, that's actually a fairly straight line. We'll have this V shape with the bottom of it at 3, -4. and we're wanting to integrate from 0 to 6. Well, here's our 0, and there's 6. What's, I guess, think about the area we've been talking about. This time it's the area under the x-axis and above the function. Whereas leading up to today, it's been the area under the function and above the x-axis. We would be looking at this part right here. Well, in this particular case, we could actually create a geometric figure, or a couple of them, to make the calculations a little bit easier, run it through our area formulas rather than going through the long process of evaluating that. There's several ways we could do this, but to me the easiest way is split it into a rectangle and a triangle. What's the area of this top piece, this rectangle? Okay, as length times width, length of 6, width of 1, we have an area of 6. And then the area of this triangle, 1/2 base, which is 6, times the height. What's the height of this triangle? Going from -1 down to -4, we get a height of 3, and we end up with area of the triangle part as 9. So the total area we get is 15. What was the value of our definite integral? -15. Well, it's not a coincidence that the area came out to be 15. We just have to realize the definite integral, if we're talking about area under the x-axis, we're going to end up with a negative value for the definite integral. If the area is above the x-axis, then it will be a positive value for the definite integral. Okay? So I guess technically we could have calculated this area and then recognize, well, the area, all of it is below the x-axis, so we could say this definite integral value would be -15, the negative of the area. Okay? Questions?
What happens if it's...
Now in this problem, we're going to be taking a look at a function defined by the graph, this graph here. Let's call this y equals f of x. And let's integrate this. Let's see, we could go either -1 to 4, or in this case, let's cut it back just a little bit. Let's go from -1 to 3. Okay. Sometimes we have more graph than we need to define here. So we're going to integrate this function from -1 to 3. Well, -1 would be right here, and then 3. What we're going to need to look at is how the area will represent what parts of this definite integral. Now, from -1 to 0, we have a little triangle. And that little triangle is below the x-axis. Okay. From 0 on over to, let's see, I think that's supposed to be 2.5. Okay, we'll say that's 2.5. We're above the x-axis. And then from 2.5 to 3, we're back below the x-axis again. So theoretically, we're going to have to split this integral into 3 parts. -1 to 0, 0 to 2.5, and from 2.5 to 3. To integrate this now, it really turns out to be find the area of each one of these regions and then apply the appropriate sign, whether it's positive or negative. So from 0 to -1, or -1 to 0, get my order correct here. The area of this triangle turns out to be what? Okay, the area is 1/2. 1/2 times the base, which is 1, times the height, which is 1. But in terms of the integral, we need to represent it as what? Okay, negative. So that part will get -1/2. Then the next part, all is above the x-axis, so area will represent the positive definite integral. And we end up with what there? Okay, this area will be 1/2. Then we have the square, which would be 1. And then the area of this triangle from 2 to 2.5 will be what? Okay. Base is 1/2. Height is 1. So 1/2 times base times height. That part will be 1/4. Add those 3 parts together and we'll get 1 3/4. Or 1.75 or 7/4, whatever form you want to write that in. And then finally, from 2.5 to 3, again, this area is under the x-axis, so the definite integral value will be negative, and that one will be what value? Again, 1/4. 1/2 times base of 1/2 times height of 1. So that would be our parts to the definite integral based on the areas. And adding those numbers together, we end up with what? Okay. That definite integral value from -1 to 3 will equal 1. And so that's how we can separate what's under the x-axis, what's over the x-axis, and represent with the graph of a function. Questions?